Okay, so good morning, everyone. I will welcome you all, and I hope that you have a great time in the next 3 days learning about this wonderful field of gravitational wave astronomy. I will be talking about some introductory things in gravitational wave astronomy that you would require to understand most of the stuff in the next 3 days. Uh, as Neha said, if you have any questions, feel free to stop me in between the talk. Uh, and with that, let me begin. Okay, so I guess we all know this, but let me say this anyway. Gravitational waves, these are the ripples in the fabric of space-time itself. So just like electromagnetic wave is a ripple in the electromagnetic field, gravitational waves are ripples in their fields, and their fields are is the space-time itself. And these ripples are produced by motion of very dense and massive objects, which are also known as compact objects, like black holes or neutron stars, when they are in a binary system and they continuously lose energy in gravitational waves, come closer and closer together, and ultimately merge. These are so massive and that they undulate the space-time, and these undulations then propagate with the speed of light, and these are what are known as gravitational waves. So far, we have detected gravitational waves from these three types of events. First is a binary black hole event, where you have two black holes. Second one is a binary neutron star, where you have two neutron stars spiraling around each other. And the third one is a neutron star black hole binary, where one of the components is neutron star, other is black hole. Uh, so before jumping on to what gravitational waves are and how you detect them and how you do data analysis, I would like to highlight some of the very nice properties of gravitational waves which make it a very appealing science probe to probe our universe and understand its nature. So gravitational waves are a very new and complementary, they will provide a very new and complementary view of the universe, in the sense that most of the stuff that we see in gravitational waves, we don't see in electromagnetic waves, that is visually, and vice versa. Most of the stuff that we see in electromagnetic waves, we don't see in gravitational waves. Okay, so in this sense, gravitational waves provide us complementary information to what we have already gathered over the past centuries using electromagnetic observations. It is also a very high purity messenger. So if you know something about electromagnetic astronomy, uh, most of the times the hurdle is that there is so much intervening medium that the signal, that the electromagnetic waves that travel to you, they get attenuated due to that medium. They get scattered, reflected, and whatnot, because they interact with the intervening medium. However, gravitational waves, it turns out, interact very weakly with matter. And therefore, they practically travel through the universe virtually unimpeded. Therefore, they carry information about their sources, which is practically free of any distortion due to the intervening medium. Third, it's a very long range messenger in the sense that when we do electromagnetic astronomy, what we detect is not directly the field. What we detect is the energy in the field or the fluxes, right? And those fluxes or energy drop off as 1 by r square. On the other hand, in case of gravitational waves, we directly detect the radiation field, which is uh, denoted by h, and h falls off as 1 by r. So therefore, you can view gravitational waves from much farther sources. Okay. For example, the first gravitational wave detection itself, it came from 400 megaparsecs away. It took centuries for us to, using parallax and whatnot methods, to reach to these distances using electromagnetic waves, using doing electromagnetic observations at these distances. But the first gravitational wave detection itself was around 400 megaparsec away. So this also makes it a very promising tool for doing cosmology, for understanding the history of the universe. As you know, light travels at a finite speed. So the farther you look, it's equivalent to looking back in time. Okay. So therefore, you can basically map out the universe to very long distances and can do cosmology using it. And lastly, and this is perhaps the most obvious one, it is an excellent probe of strong gravity. As I just said, these gravitational waves that we are detecting them from the collisions of black holes, neutron stars, and so on. And all these sources are very dense and very compact. So when they merge, they produce some of the strongest and most the highest energies possible in the universe. For example, and okay, so for example, here I am showing you an infographic. So this event GW150914 was the first gravitational wave event, and here I am showing the black holes size to scale. These black holes were around 30 solar mass each. So each of these black holes have 30 times the mass of the sun, but they are fitting on the map of India conveniently. So much mass, yet in such a compact location. When they move around each other and then ultimately merge, they produce very strong vibrations in space-time, and you can probe very high energy physics using gravitational waves. In fact, when they merged to form this bigger black hole. And if you sum the individual masses of these black holes, you will find that it is not equal to this black hole's mass, this final black hole's mass. It is larger by 3 solar masses, which means that 3 solar masses of energy of mass was completely converted into energy, which is equivalent to 50 times the total energy output, total EM energy output of the entire observable universe. 50 times, just through one single event. Okay. So GW astronomy is around a decade old now. Some of the feathers in the cap are as follows. It showed the existence of heavy stellar mass black holes. So as I said, the very first detection itself was from black holes, which were around 30 solar masses each. Previous to this detection, people didn't really believe that such high mass black holes can form through stellar evolution. There are mechanisms, but most of the primary consensus was that most of the black holes are around 10 solar masses and so on. But it turns out that most of the binary black hole events are around 30 solar masses. The component masses are 30 solar masses. This showed the existence of such heavy stellar mass black holes. In fact, a fun fact is that before we had made these gravitational wave detections, binary black holes were not even the strongest contenders, were not even thought of as the strongest contender for gravitational waves. People thought that the first events that we will see through LIGO will be binary neutron stars. And unfortunately, we have detected around 218 gravitational wave events, and only 2 or 3 of them are neutron star events. And I guess less than 10 of them are neutron star black hole events, and rest all around 200 events are binary black hole events. So again, nature surprises you. This second event, GW17817, this was a binary neutron star merger. It was observed both in gravitational waves and electromagnetic waves, and is perhaps the most studied astronomical event in history of science. And this event in particular showed that most of the heavy elements in the universe are formed through collisions of these neutron stars. For example, gold and platinum. This event also showed that there is an event known as short gamma ray burst, as the name suggests. There is a burst of gamma radiation. We didn't really know exactly what are the possible sources of these short gamma ray bursts, but this particular event produced it. So now we know that binary neutron stars at least are a plausible mechanism to produce these short gamma ray bursts. Then very recently, only last year, we observed this event GW250114. It is the strongest gravitational wave event so far. And therefore, it allowed us to do most stringent single event basis verification of general relativity. So for example, we uh, put the most stringent uh, conditions on the Kerr nature of the remnant black hole. So the final black hole, whether it's a Kerr black hole or something else, this particular event proved that to a very high degree it is a Kerr black hole. A Kerr. By the way, how many of you have taken a GR course before? Okay, so when I say Kerr black hole, do people understand what I mean? Okay, how many of you don't know what I mean? There is no shame. Oh, okay, okay, okay. So Kerr black hole is a category of black holes which is rotating, which is spinning. So a spinning black hole is known as a Kerr black hole. It is named after the person who found this rotating black hole solution, Roy Kerr. So, okay. This event also allowed to test the Hawking's area theorem to around 4 sigmas. Hawking's area theorem says that basically that uh, the combined area of the two black holes has to be I'm sorry, I have written this wrong. I'm so sorry. So the combined area of the two black holes should be, so the area of the final black hole should be larger than the combined area of the individual black holes. So this is the Hawking's area theorem. It is basically a restatement of second law of thermodynamics, which says that entropy of a system always increases. It can never decrease. And it was found that entropy of a black hole is proportional to its area. So that's where it comes from. And we have many more events. So for example, there through the stellar evolution theory, we know that there should not exist black holes in this mass range called the lower mass gap, which ranges from around 3 solar masses to 5 solar masses. Then there are also there also exists an upper mass gap, which is around 100 to 150, if I remember correctly. So stellar evolution theory tells us that black holes of these particular masses or in these ranges should not form. And we have detected black holes in these ranges, in both these ranges. So again, we don't know how these are formed. So these are some of the surprises and some of the nice results that gravitational waves have given us in just 10 years of its results. And we have detected 200 events so far, and we are counting. Okay, so doing all this requires cutting edge engineering to detect these feeble gravitational waves, advancements in theoretical understanding of GR, as we'll see. Unless you know what kind of waveforms, gravitational waveforms, you can expect to detect, you cannot even detect gravitational waves. We'll see what I mean by this. And we also require very sophisticated data analysis techniques because gravitational waves are very feeble, and it turns out that even after so many engineering advancements, gravitational waves remain shrouded in instrumental noise. So you have to apply some data analysis techniques to bring it out of this noise. So this talk will focus on what are gravitational waves. Then I'll go on to discussing very briefly how we detect them. Then I will talk briefly about how we analyze GW data. And during my whole talk, I will point to the various things that you will learn throughout the workshop. Okay, so what are gravitational waves? Since I just did a poll and not many people knew GR, okay, how many of you have done special relativity? How many of you have not done special relativity? Sorry. Just let me think. Okay. Okay, those who know GR, it's fine. Those who don't know GR, it's fine if you don't understand anything till I discuss this equation. Okay, just ignore what I'm saying. For you, gravitational waves are just another kind of waves. Okay, just let me go through it and then we'll see how it turns out. So gravitational waves are fluctuations of space-time, as I said. And this is space-time I will denote by h. And this turns out to be a tensor. Okay, so just like vector has three components, a tensor, depending on the number of indices, can have varying number of components. This in particular is a rank 2 tensor. So there are two indices in it. A vector in tensorial notation will have only one index. So if I have to describe a vector, for example, dx mu, here you are seeing this is a vector. It has just one index. Okay. So this ds square is the line element. G mu nu is known as the metric of the space-time. What Einstein taught us is that gravity is not what Newton thought, what we were told as by Newton. What Einstein taught us is that gravity is nothing but the curvature or geometry of space-time itself. Space-time. Okay, so it's a combined entity, first of all. Space and time are not separated. I am talking about combined entity called space-time. And what he basically taught us that whenever you have some mass or whenever you have some energy, it distorts the space-time around it. And all the gravitational influences, for example, orbits of planets, etc., all these things that you see are nothing but free motion of all these objects on this curved space-time. Okay. So these, so what I'm trying to say is that the curvature of space-time and presence of energy or mass there is equivalent. Mass, energy produces a space-time curvature. Okay. This is what this equation is. So on left-hand side, okay, and this curvature is measured by this G mu nu. Okay, this G mu nu is known as the metric tensor. It basically tells you how to measure space-time distances. Okay. So this left-hand side of this equation, it's a very complicated stuff. I have just denoted it by capital G. It has derivatives and whatnot of G. This left-hand side quantity completely depends on the geometry. This right-hand side is something known as the stress energy tensor. This contains all your masses, energy, sources, pressure, etc. So this equation tells you the same thing that I just said in English, is that matter or energy produces curvature in the space-time. Okay, and this gravitational wave is nothing but this G mu nu, which is the metric which tells you how the space-time curves, expanded around the flat space-time. A flat space-time is a space-time where no mass or energy exists. Okay, so it's devoid of any mass or energy. Then the space-time is said to be flat. And this eta mu nu is the metric of that flat space-time. So gravitational waves, h mu nu, are defined as perturbations of metric tensor around flat space-time. Okay. So this flat space-time is basically the zero of this field. Okay. So just like for electromagnetic waves, a zero would be a zero vector. Here it won't be a zero vector. Here it would be a flat space-time, eta mu. That's all. It turns out that when you plug this thing into these equations, these are known as Einstein field equations, you get this equation. Do people know about this box operator? This box operator is called the D'Alembert, and it is nothing but this operator. Grad, do people grad know grad and all? Okay, oh, cool. So this is the D'Alembert operator. This is something known as the wave equation. I guess you must have seen wave equation. Okay. And that's why when you solve it, you get wave equation like solutions. Okay. So you have an amplitude. Again, it has two indices because the gravitational waves are a tensor. So this is also a tensor. And then you have the usual exponential factor that you have in a plane wave. Just like EM waves, it turns out that gravitational waves are also transverse. That is, there are no oscillations along the direction of propagation of gravitational waves. Okay, this is that condition. So this is nothing but your usual k vector dot E vector equals 0. K vector dot B vector equals 0 in case of electromagnetic fields. This is just a tensorial version of this equation. Wherever you see two indices, they are summed over. Okay. Okay, let me not get into the details of it. Otherwise, I'll have to explain all the conventions, etc. Einstein summation convention. Okay. And just like electromagnetic waves, gravitational waves also turn out to have two polarizations. So just like an electromagnetic wave can be decomposed into two polarizations, you can also decompose gravitational waves into exactly two polarizations. These polarizations are called H plus and H cross. Okay. And the effect of these plus and cross polarization is shown in this animation. So suppose you have a ring of particles, and suppose a gravitational wave is passing through this screen perpendicularly. Then if it is the plus polarization, you will see stretching in perpendicular directions, once in vertical and squeezing in horizontal, and vice versa. Okay. And the cross polarization has the same thing but at 45-degree angle instead of being at x and y axis. And this animation shows the plus polarization in 3D. So it shows that the gravitational wave is propagating in this direction, which is perpendicular to the oscillations of the ring of particles. Okay, so this is basically what gravitational waves are. Again, if you didn't understand most of it, just remember that it's just a wave. Okay, just like EM electromagnetic waves are waves. This is also a wave. Just like electromagnetic wave is transverse, this is also transverse. Just like electromagnetic wave has two polarizations, gravitational waves also have two polarizations. That's it. Okay, now I'm thinking that I should skip this. Okay, let me very briefly go through this. I won't explain the equations. So it turns out that to leading order, gravitational waves are produced by what is known as the mass quadrupole moment. Okay, so just like in electromagnetic case, you must have heard of dipole moment. So in dipole moment, you multiply the charge by a distance, right? For quadrupole moment, you again multiply, for mass quadrupole moment, here the analog of charge is mass. You multiply mass or density integrated over and multiply it twice by the distance. Okay, this is a mass quadrupole moment. And it turns out that gravitational waves to leading order are sourced by double derivative of this mass quadrupole moment. Okay. Those who have learned about tensors may have seen this equation. This is nothing but the moment of inertia tensor. Okay. Anyway, doesn't matter if you don't know about it. Then, if you do some maths for a binary moving in the xy plane in a circular orbit, uh, what you will find is this expression for h plus and h cross. Doesn't matter, all these details don't matter anymore. What you will find is that the gravitational wave is proportional to this particular thing. So those who have taken a GR course, I will tell you a very useful mnemonic. So you write this equation as this. Do people, those who have taken a GR course, do people recognize what this thing is? Right. So this is a Schwarzschild radius like quantity. Okay. This is nothing but the Schwarzschild radius of a black hole of mass capital M. Okay, I didn't mention it here. Capital M is M1 plus M2, the sum of both the masses. Mu is the reduced mass. Okay, and similarly, this also looks very much like. Uh, sorry, I missed the c square divided by r. Here, capital R is the extent of the source itself, and small r is the distance of the source from the observer, for example, us. Okay. So, and if you calculate this thing for a typical binary of around 10 solar masses, which is situated at around 100 megaparsecs away, you will find that this gravitational wave is of the order of 10 power minus 21. By the way, gravitational, this h is a dimensionless number. Okay. Now, I don't know whether I should go. Okay. From here, I will go here. What you will find is that this h plus and h cross has this piece 2 pi fgw t ret. I just want to, so this is a sinusoidal function which has frequency fgw. It just so turns out that fgw, which is the frequency of motion of this binary, sorry, fgw is not the frequency of motion of this binary. F orbital is the frequency of motion of this binary. And it turns out that this FGW is twice this orbital frequency. So what it tells you is that if the frequency of motion of object is F, then the frequency of the radiation will be twice of it. Okay. Now, due to gravitational wave emission, the system radiates away energy, and this is the formula for the power, that is energy radiated per unit time. Due to this power loss, the system loses energy, the orbits shrink gradually. This speeds up the binary. Why does it speed up? It's just Kepler's law, right? Which is this. And then there is an increase in the gravitational waves frequency, because the frequency will also increase. And this is how the frequency increases. All in all, when you will solve this equation for FGW and put it in here, you will find that H plus and H cross are sinusoidal functions whose frequency gradually increases. This is known as a chirping signal. And this here shows such a chirping signal. On y-axis is plotted the frequency of the signal. On x-axis is plotted the time. This is known as a spectrogram. You will learn about it in tutorial 3.3. It's just a frequency time graph. So as you can see, the signal here starts with a low frequency, and as we evolve in time, the frequency gradually increases. Okay, so this is just what I explained now. This was, by the way, from the first gravitational wave detection. Okay, so how do we detect them? So gravitational waves, as I said, it was a component of the metric tensor, and I told you that metric tensor is used to compute distances in space-time. So it means that when you have a gravitational wave causes changes in space-time. Okay. What this means is that gravitational waves, when they pass through something, they change the distances, or basically they change their lengths. Okay. And in particular, gravitational wave produces strain. Strain is basically fractional change in the length. Okay. And we use this fact to detect gravitational waves by using Michelson interferometer. So we see Michelson helping Einstein once again. Those who don't know the story, special relativity, the existence of the Michelson-Morley experiment proved the non-existence of this mysterious fluid called ether, which flowed throughout the universe, and people thought that electromagnetic waves are oscillations in this ether. And Michelson-Morley proved that it is not the case. Electromagnetic waves travel through vacuum. They can travel through vacuum. So we see that, and he did the same thing. He did an interferometric experiment. And again, right now, we detect gravitational waves using Michelson interferometer. So we have this instrument called LIGO. Its full form is Laser Interferometer Gravitational Wave Observatory. It has two perpendicular arms. Each of these arms are 4 kilometers in length. What happens is we shoot lasers into these two perpendicular arms. There is a beam splitter. It splits the laser coming from this laser, and it goes into the arms. And at the end of the arms, there are two mirrors. Okay, so one here, one here. This laser gets reflected from that arm, recombines here. Okay, and when it recombines, it interferes. When there is no gravitational wave passing by, it so turns out that there is a complete destructive interference. Okay, so when there is no gravitational wave passing by, you will see nothing. Okay, at the photodetector. But suppose a gravitational wave passes by. Gravitational waves then produce strain. Due to strain, the length of these interferometer arms change, and they change by different amounts. I just showed you an animation of the plus and cross polarization. You see that if one direction stretches, the other one squeezes. So therefore, if one arm stretches, the other one squeezes, and so on. Therefore, light has to travel different path lengths in both the arms. And when they recombine, they now don't totally destructively interfere. There is some finite interference pattern. And you use this interference pattern to detect gravitational wave. You use it as a proxy for gravitational wave detection. Now, let's do some back of the envelope calculation to sort of admire the feat of engineering that all this requires. So we just calculated that a typical gravitational wave amplitude is around 10 power minus 21. The length of these arms is 4 kilometers. So, and gravitational wave is equal to strain. So what is the relative change produced in the length of the arm? It is 1000 times 10 power minus 15 meter. 10 power minus 15 meter, as you might know, is like width of a hydrogen nucleus, which is nothing but a proton. So you have to measure distances 1000th, change in distances 1000th of the width of a proton in order to detect these gravitational waves. Okay. So I'm skipping over a lot of engineering that goes into making these arms. There is power recycling. There is a Fabry-Perot cavity, which effectively turns this 4 kilometer arm length into 1200 kilometer arm length and so on. I am skipping all those details, but just you understand that this, it is just amazing that we are able to do something like this. We are able to detect gravitational waves. So in this sense, gravitational wave detectors, all of them, are the most precise rulers ever constructed. Again, some more facts about the feat of engineering this requires. Uh, Here is the real, one of the real LIGOs, which is in Livingston, USA. And you see there is a tube. You have to, and it is through this tube that these lasers pass. You have to create a very high vacuum inside these tubes because the laser power is so much inside it that if there are molecules, they will scatter. So first of all, laser will lose power. We need power, it turns out, to do these detections well. And secondly, if even a speck of dust falls on, say, one of the mirrors, these mirrors are very high quality, very highly polished mirrors. If a speck of dust falls on it and this high power laser then falls on that speck of dust, it will vaporize it, and in process it will damage the mirror. So you have to maintain a very high, very high quality vacuum. And it turns out that these LIGO detectors are the second largest ultra high vacuum facilities, and it is surpassed only by the Large Hadron Collider. Okay. This also employs one of the most stable and pristine lasers ever created. So as I said, it relies on interferometry of lasers. If the wavelength of the lasers even fluctuates a little bit, it's like you have a ruler and its millimeter markings are fluctuating every once and then. So how will you make a measurement? That's why you need very stable, very precise lasers, and LIGO lasers are one of the most stable and pristine lasers present on Earth. It also has one of the smoothest mirrors in the world. It has flatness of better than 0.5 nanometers. Okay, and it's literally built nanometer by nanometer when it's constructed. Even after all this, if this doesn't wow you, I will now talk about the sensitivity of these detectors. These are sensitive for gravitational waves, which have frequencies in the range 20 to 2000 hertz. Okay, and it is shown in this plot. This plot is something known as the power spectral density plot. We will learn more about this in tutorial 3.1 and 3.2. What power spectral density basically means, as I said, there are lots of noise. There is lots of noise in the detector. Assume a time series of this noise, and then try finding correlation of each of these series points with each other. This power spectral density is nothing but the Fourier transform of this correlation. So what it tells you, if there is a peak at any point in this frequency, so for example, you see one peak here, this is around 60 hertz. Okay, it means that the noise in these detectors have some correlation at 60 hertz. So every 1/60th second, there is some positive correlation or negative correlation between the noise chunks. Does anyone have any guess why 60 hertz? Have you heard of 60 hertz? Have you heard of, okay, I won't give any more hints. Here it's 15. Okay, so in US, the alternating current supply is at 60 hertz. This line corresponds to that 60 hertz line. Okay. Then there are other such lines also. These are known as violin modes. These mirrors that I told you are at the end of the interferometer arms. They are suspended by very thin silica fibers. Uh, and these are then further suspended through pendulums. And it turns out that these frequencies are the resonance frequencies of these pendulums. Okay. Now, this black curve shows you the net power spectral density. Let's see what lines basically are limiting our current sensitivity. So it's this orange line and it's this blue line. Let's read their labels. The blue line says quantum shot, the orange line says quantum radiation pressure. So both of these have quantum in them. What it means is that at such macroscopic levels, at such macroscopic detections, these instruments are so precise that quantum level physics is entering and ruining our measurements. These are those so sensitive. Uh, I won't discuss in detail what these are because we are running out of time. Uh, if we have time, we'll discuss them during the tutorials. And these are continually upgrading. So these represent the science runs. So these are labeled as O1, O2, O3, O4, and so on. The newest one, which is the planned one, is known as intermediate run. So it's called IR1, but anyway. And here you can see the distances to which each of these detectors could see binary neutron star mergers over some averaged distance. The details don't matter. What matters is these numbers are increasing in every run. So these are being continuously upgraded. And yeah. Now, as I said, gravitational waves interact very weakly with any intervening matter. So therefore, when a gravitational wave comes through the Earth, it just passes through the Earth. It means that a gravitational wave detector does not need any pointing, like EM telescopes. You have to point towards a star to see the star. You don't need to point a gravitational wave detector because a gravitational wave, even if it's coming beneath the Earth, it will just pass through you. So in this sense, gravitational wave detectors are omnidirectional. Okay. However, this does not mean that you can just do away with a single detector. You need multiple detectors in order to localize the source as well. So this is known as triangulation. Some of you may know that you require three different measurement from three different instruments using their time of arrival. You can then triangulate or pinpoint the object well. So for example, this particular plot shows exactly that for this particular event GW17070. What this shows you in blue are the regions in which this event was localized just by two detectors, Hanford and Livingston. So this is Hanford, this is Livingston. Both of them are in US. Then in green here is shown the case when you have three detectors observing this event simultaneously. This V is Virgo, which sits here near Pisa, Italy. As you can see, the sky area is much better. And then the gray bands basically show the three detector pairs. So Hanford, Livingston, Hanford, Virgo, Livingston, Virgo, and so on. So this. Now, these are some of the operational facilities. So you can see 5 of them. Unfortunately, this guy is going to get decommissioned later this year, at the end of this year, GEO 600. But you have also a planned LIGO, which is in India. So this is again another motivation for you guys to learn more about gravitational wave astronomy. You might find your future in this. Okay. Another nice thing about LIGO India is that it sits almost exactly opposite on globe to America. This gives it a very long baseline. And the more distant the detectors are, the more well you can localize the sources. So therefore, when LIGO India becomes online, we will have much better sky localization than we have currently. Another advantage of having more detectors is also that multiple detectors help us in vetoing out false triggers via coincidence tests. So, as I said, there is a lot of noise in the detectors, and this noise also sometimes can mimic a gravitational wave signal. Okay, so if you had only one detector, you would just plainly believe that it's a gravitational wave, right? But if you have two detectors, then it's very unlikely that at the second detector, the same kind of noise happened and produced the gravitational wave, and mimicked the gravitational wave, not produced the gravitational wave, mimicked the gravitational wave. Why? Because these are noise. Noise between two detectors can't be correlated. Okay. Only if you have a real gravitational wave signal, it will pass through both the detectors, and there will be some delay time between them depending on how far they are. So that's how you can veto out false triggers that have been triggered through this false identification of noise as a gravitational wave. And these are known as coincidence tests. You check whether the same gravitational wave passed through multiple detectors or not. This will be covered in tutorial 4.3 more deeply. Okay. My lecture was supposed to be till 10:45. Oh, God. Okay. I will wrap up quickly. How do you then do science with gravitational waves? So even after all this engineering, it turns out that most of the gravitational wave signals still remain shrouded in noise. So for example, this shows one of the loudest gravitational waves that we detected, which is the first gravitational wave event. And the true signal is in orange and blue. And as you can see, there are many oscillations here. Uh, while the true signal, which has been regenerated by what is known as a waveform model, I will describe more about it, is in black. And as you can see, black is much more pristine looking than these orange and blue curves. So what to bring these gravitational waves which are hidden in these noises, what you do is you cross correlate your data with the kind of waveform that you expect to see. Okay. And these waveforms are created by using our theoretical understanding of the two-body problem in general relativity. Okay. So one of the examples of this we did just now when I was explaining gravitational wave sources and when I was explaining that its frequency is twice the orbital frequency and so on, that it's a sinusoidal signal. All this comes from our understanding of how gravity behaves. So these are known as theoretical template waveforms, and these are generated by what are known as waveform models to estimate the properties of the systems that created these gravitational waves. It turns out that there are 15 parameters to look at for a binary which is in a circular orbit or a quasi-circular orbit. We call it quasi-circular because as we just discussed, it in spiral, so it's not a closed orbit. It spirals. That's why it's called quasi-circular. What are these parameters? There are 8 intrinsic parameters. These are the masses, 2 masses, and spin vectors. So as I said, these black holes can also be spinning, and each of these is a vector. So these are 6 quantities. Then there are extrinsic parameters. This phi c is known as the phase of coalescence. It is nothing but uh, yeah, nothing but an additional phase here. You just do plus phi c here. So it tells you the relative, uh, the phase with which the gravitational wave starts. Okay, sorry, I completely forgot to mention why are they called intrinsic parameters. These parameters depend on the source. Extrinsic parameters are not a property of the source. Extrinsic parameters depend on when we detected the gravitational wave, where we detected the gravitational wave. So it depends on the relative location of us and our detectors with respect to the object. So it's not a property of the object. It's right. The psi is known as the polarization angle. Just like you can decompose electromagnetic waves around axes of your choice, you can also decompose gravitational waves in plus and cross polarization around axes of your choice. This choice of axis is encoded in this parameter psi. I is the inclination angle. So the angle of your line of sight, angle between your line of sight to the object with respect to the orbital angular momentum of the object. Okay, so suppose you detect a binary here, which is moving like this. And if its angular momentum direction is this, and suppose you are watching from here, then this is your line of sight, this is the inclination angle I. And then the other thing is the space-time location of the event. So there are many ways to measure the location of this of an event. One thing you need is obviously the distance to the event, and also you need two more angles. These could be the right ascension and declination. This PC is the time of coalescence. So just like phi c was an additional factor in the formula, you also have a reference time. So it encodes when the gravitational wave arrived at us. So this is for a quasi-circular system. If you want to detect more physics from your gravitational waves, you have to include more physics into your waveform models. More physics like eccentricity. What if the orbits are eccentric? It also turns out that for an eccentric signal, you need another angle called mean anomaly. Then if you have a neutron star can also get tidally deformed, just like we have tides on Earth due to bulging of Earth, due to sun and moon. This neutron star binary, both the neutron stars can exert these tidal forces onto each other. And these tidal deformability parameters then compute how squishy they are, basically, how deformable they are. Okay, I will skip this. I wanted to show you how you can try doing this matching to data of a waveform model yourself. So in this sense, theoretical gravitational waveform models are therefore the cornerstone of gravitational wave astronomy. Without knowing what you are looking for, you cannot really detect a gravitational wave. Okay. Okay, so these waveform models are constructed in the following manner. There are three separate regimes. The initial regime, when the black holes or any compact object is farther, it is moving slowly as compared to speed of light. This phase of binary motion can be successfully captured via what is known as the post-Newtonian theory. It's a perturbative theory in this parameter v by c, where v is the velocity, relative velocity of the two objects, divided by c, the speed of light. So it's a perturbation series. Since it's a perturbation series in v by c, it will break down as soon as velocities start reaching close to speed of light, which is when they are just about to merge. So this thing only works till they are very close to each other. After this, you can no longer use this post-Newtonian theory. After this, what you need is true, fully non-linear solutions of Einstein field equations. And these are done numerically, and the field doing this is known as numerical relativity, in which you solve these Einstein equations exactly on computers. And then the third part is when you form the black hole, this final black hole is highly distorted, and it settles into its undistorted state by ringing like a bell. And this ringing produces this portion of signal after the peak, which is the moon. So this is a numerical relativity simulation of the first binary black hole event, which was called GW150914. And as you can see, this has formed, and then after it formed, there were more gravitational waves which were emitted because the black hole was highly distorted. These colors represent how strong the gravitational field is, basically. Okay. Here I am showing you some, depending on what parameters you feed into the waveform model, how does your waveform look and change. So for the top three things are for quasi-circular systems. So systems which are on circular orbits, whose spins are either aligned or anti-aligned with the orbital angular momentum. Okay. So in the first panel, you see that both the spins are along the orbital angular momentum, which is this central arrow. In the second one, there are no spins on the black holes. In the third one, there are opposite spins to the angular momentum. And as you can see, the major effect that this produces is that this waveform produced is longer. This is slightly shorter than this, and this is the shortest. So this is one of the differences, right? So having more spin along the angular momentum makes your waveform longer. I don't have time to explain this, but if you are interested, you can talk to me later on. This is known as the orbital hang-up effect. Right. Then this second one, in the second one, the black hole spins are misaligned with respect to the orbital angular momentum. In this case, the plane of the orbit precesses, just like a top. Okay. And the spins also precess. And the morphology of the waveform now is significantly different from the waveforms you saw here. So again, depending on the parameters, these things will vary. And you will learn more about this in tutorial 2.1, how to generate these waveforms for yourself, for example. You can similarly add eccentricity into the mix. Eccentricity produces modulations in the amplitude and also in the phase. So now the binary at its nearest point moves the fastest, goes away, then again comes close, then goes away. So when it's going away, there is slight stretching in the waveform. When it comes back close together, there is a squeezing. And it also emits more radiation when it's close. So there is a higher amplitude also there. So this is how eccentricity goes. I don't have enough time to cover this. I guess Priyanka will cover it on my behalf. Okay. So yeah, this is, I will just quickly wrap up on this. So gravitational wave data analysis is done in two stages. In the first stage, which is known as the matched filtering stage, or known as search, we ask the question whether there is a signal in the data stream at all. We don't care much about its properties, exactly what its source properties are. We just want to know whether there is a signal in the data or not. So this search has to be done over the whole data stream. As the data is coming through to you, you have to do this search. These searches use less accurate but fast template waveforms to do this fastly. Therefore, these are computationally cheaper. You can therefore get faster alerts and then, for example, quickly alert if there is a gravitational wave event. You can alert, for example, EM telescopes to quickly slew over to that event so that they can look for any possible EM counterpart. However, you don't get very accurate source parameters. So therefore, once you have found that, okay, in this particular chunk of data, I have found a gravitational wave. Then you do it more rigorously. Then you analyze that chunk of data more rigorously. It's known as parameter estimation. And you ask the question, what exactly is that gravitational wave? So as I said, this is done over a small chunk of data. It uses the best waveforms available, and therefore it can be slow. And it is computationally expensive. But it gives you the most accurate or best measurement of source properties possible. I won't cover this, but I will just quickly highlight the broad idea of this. So what you basically do is what I just told you 2 slides back, is you have data, then you cross correlate your data with a template waveform. If you don't find anything, you slightly change the parameters of the template waveform and then cross correlate with this new template. And you keep doing this again and again. until you find that some particular template again matches the data well. So here you are basically sliding this template over the data, and it turns out that at this particular point there is a peak. Okay, when you cross correlate this data, this gives you a trigger, and then you know that okay, there is a gravitational wave. I won't discuss this formula, this will be discussed in the tutorial. And then you do parameter estimation. Once you know that the signal is there, what you do is you analyze that piece of data using what is known as Bayesian inference. Right, it will be covered in the tutorials again. Uh, it basically employs Bayes' theorem to figure out the parameters of the source given the data. I won't cover this in the interest of time. The problem here, and this will be explored in the tutorial, is that in this you have to, so what you get out of this Bayesian inference are probability distributions. And the problem here is that you have to sample probability distributions over 15 parameters. So you have to sample 15 dimensional parameter space. And this becomes very computationally expensive. So what you use are known as stochastic sampling techniques, which will be discussed in tutorials. Without these stochastic sampling techniques, Bayesian inference would have not been practical. Uh, this is a very useful skill, by the way, to have. This is not just used in gravitational wave astronomy, it's used ubiquitously across many fields in physics to do inference, and also in finance and whatnot. Once you have these probability distribution over the source parameters, for example, masses, you will get a distribution. Then you can do whatever you like. You can compute median, you can compute the error bar ranges in 1 sigma, 2 sigma, whatever, and so on. So this is a particular probability distribution that you guys will produce in one of the tutorials. So that is it. I think you guys can cover the workshop logistics, or I can cover it. Okay. Okay. So these tutorials here are on GWOSC. So do you guys know where all these tutorials, etc. live? Have you already signed up for this Thinkific course? How many of you have not signed up for it? Okay, a majority of you. Okay, so let me show you. So go to gwosc.org. Once you are there, go to Open Data Workshop 2026. Right. Now, I have already enrolled in it. You will get an option of enrolling yourself. Okay, so you just have to log in through one of your email accounts and so on. Once you have done so, you will be taken to this page. Okay, so this is the Thinkific platform. This is where you will get access to all the tutorial problems. For example, the first tutorial would be on accessing the open data. So here you will get the link to the tutorial. This will open in GitHub. If you are familiar with GitHub, you can just clone this repository and do it locally on your computer. Or if you are not that tech savvy, you can just do two collab here. So after GitHub, you just add two collab. Okay. How many of you are on this page, by the way? How many of you are left out? left out? Can you quickly do this? Okay. Till where? Is this fine or? Okay, let me go through it again. So you are on ghost.org, right? From this, uh, where? Go to the GitHub page. Okay. Yeah, it can be. Yeah, this is already collab though. Yeah. Right. So if you, if you don't want to do this two collab thing. Right. So how many of you are now on this page? How many of you are not on this page? Okay, none of you. So then you click on either resume course if you have already signed up for it, or otherwise you will be directly taken to this particular web page. Once you are here, you can go to one of the tutorials, the very first tutorial in the accessing open data part, and you can click on this link. This is the link to the tutorial. How many of you are not on this page? Okay. Oh, you are not on this page? Okay. Yeah, by clicking on this link. Yes. So are people able to open this GitHub page? How many of you are not able to open this page? Yeah, do let us know. We can help you guys. Not so much. Okay. So after this, I said that uh, if you people know how to, if you want to run all these locally, you will need to either just download these notebooks or just clone the full GitHub repo. Or if you don't want to do any of that, you can just click on this Google Collaboratory link here. Forget about what I said about changing the link to GitHub to Collab. And once you are here, you can just run these notebooks, all your code on this web page. Just make sure that there are some comments here which say that if you are running this on Google Colab, you should uncomment them. So just when you are doing tutorials, you just uncomment them. I accidentally uncommented the comment. Okay. Yeah. Okay, so that's how you will access all the tutorials. Um, right. At the end of each tutorial, there will be a few questions. Those questions are the same questions which appear here on this portal as quiz. So you, after you do each tutorial, at the end of them, when you answer them, don't answer them just on the notebook. Also fill your answers in here. Okay, so that's the basic plan that you have to follow for each tutorial. At the end of it, just to challenge yourself whether you have understood all this stuff that we teach you in the next 3 days or not, you can try this data challenge. Okay, this won't be done by us. This is something up to you. And if you are interested, you can again find notebooks, etc., questions and all. And you have to submit this data challenge on this website by 3rd May. And I think they get some certificate or something. I forgot what the criteria was. They get something, right? Yeah, you will get some certificate of sort if you complete this data challenge successfully. So yeah, that's it. And now we will break for coffee for how many minutes? Okay, let's come by 11:30. Feel free to discuss these things amongst yourselves or catch some of us if you have any questions. Please be very respectful when you are talking to people and maintain a collegial environment so that it's a fun experience for all of us. Okay, so let's break for coffee.